Okay, well, good morning, afternoon, evening. Uh, Derek asked me to talk about what I've done with GNU Radio, and I thought focusing in on one project would be really interesting because it exposes a number of different disciplines and aspects of the hobby and how ham radio can be very relevant for science and academics. Uh, so in 2017, we had a solar eclipse. And there we go. Total eclipse that passed over much of the US in August of 2017. And that aroused a lot of interest among the space science community because it gives an opportunity to see what happens when the ionosphere goes rapidly from daytime to nighttime and back again. And the theory is that there would be various propagation impacts of that. In 2016, Nathaniel Frizzell, W2NAF, who at that time was a professor in the physics department at New Jersey Institute of Technology, started putting together a group called HamSci with the idea of doing citizen science projects in a very informal collaboration between space science scientists and hams. And there's a number of people who are in both of those camps. And Nathaniel's first focus was on the eclipse as the possibility of crowdsourcing scientific research by using the ham radio activities. So they did a number of things during the prior to the eclipse to try to stir up interest. The biggest one was they sponsored an HFQSO party. Just get on the air, make as many contacts as you can. And the idea behind that was that people just submitting their logs would be able to provide useful information about what paths were there at given times and how the activity changed. In addition to that, they make great use of the reverse beacon network and the PSK reporter for picking up spots from digital modes. You know, there are literally billions and billions of spots that have now been recorded with each end of the path, the date and time, and signal to noise ratio. So there's actually a gigantic amount of data in that system. There was also interest in doing Doppler measurements because we know that as the propagation changes, as the ionosphere switches from daytime to nighttime modes, the reflective layers raise and lower, which changes the effective path length, which results in a Doppler shift in the frequency. So there was a desire to see how that impact might show up during the eclipse. And then there were other ideas that people had, and also something of the we don't know what we don't know. So that led me to become interested because I thought that using software-defined radios, we could do wideband data recording to pick up an entire ham band and save it to disk so that we could come back later and process it and wring more data out of it rather than just using real-time logging information or even the recorded PSK beacon reports. We actually have the IQ data for the ham band. We have or at least until recently, had a cottage in far northern Michigan where we vacation, and I was going to be up there during the latter part of August, which was not the ideal location for the eclipse. I'll get to that in a moment. But I decided I'd haul the equipment up to try to do broadband recordings of several of the ham bands for several hours around the eclipse, and also record the AM broadcast band to see if information could be gleaned from using a broadcast station for looking for Doppler and amplitude shifts and things. So the only problem with my scheme was that the total eclipse path passed kind of through the middle of the US, and you probably cannot see it, but if you look very carefully just under the between the S and the T in August, I'm sorry, no, that's off. Underneath the two in 2017, there's a little box And there's an island out in the northern part of Lake Michigan called Beaver Island, and that is where I was. And it was not the ideal location because we were several hundred miles away from the total path, but it also seemed like an interesting location, and Nathaniel assured me that we would see propagation impacts even far away from the totality line. So this is a little bit more about the island. It's about 8 by 13 miles in dimensions. Our cottage is on the far eastern shore, about 3/4 of the way down. There's another little red dot there that you probably can't see. Uh, and it's a very interesting location. It has extremely low RF noise. At the time I was there, there was only one other occupied house within 500 feet. There were no high voltage lines around, and there were no powerful signals nearby. Uh, the only transmitters on the island were an aeronautical beacon that was about 5 miles away, and public service, police and various things like that. And their repeater was about 3 or 4 miles away. The nearest broadcast station was 25 miles away across water. And according to the radio locator, I was only supposed to be able to hear 8 AM stations. Well, this past summer, I took a much better receiver up, and during the daytime, I was able to copy a signal on at least 2/3 of the AM broadcast channels, because with the lake as the ground around me, I was hearing Chicago, Milwaukee, Detroit, Toronto. It was just incredible how many stations we could hear because of the very quiet location. Now, there were very few other local ham stations around to provide a reference point, so I was kind of on my own there. And the northern location kind of puts us far away from everything. It's about 260 miles up the lake from Chicago, and for operating VHF, it's interesting because it's a fairly rare grid, but nobody ever points their antennas in my direction because I'm so far north of almost everyone. So that was a little bit of a downside. But again, it seemed that it might work out as a good place, particularly because of that low noise level. So I created my scientific research station in the spare bedroom of our cottage, and I had a Hermes HPSDR along. That's the single board transceiver that was the main product that came out of the high performance SDR project. And I used it to record 80, 40, 30, and 20 meters. I had the older Atlas Mercury SDR receiver that I used with some non-GNU radio software called KISS Console to just record a wideband spectrum dump. I wasn't able to get IQ data, but I could get at least amplitude and frequency. And then I also had a red Pitaya, and I was going to use that for AM broadcast band, but it also received the 160 meter band along the way. I had a 43-foot vertical antenna for the HF bands, and about a 50-foot wire shot up into a tree that was used for the red Pitaya for broadcast. Because I am a time nut, I hauled a cesium frequency standard along, and that provided the frequency reference for the HPSDR radios. So we knew that they were on frequency, and any shifts that we saw were Doppler or something like that, rather than my local oscillator. And I had 3 radios, so I had 3 computers. 2 of them were i7 laptops, and one was an i5. The CPU speed really wasn't an issue for what we were recording. None of the receivers seemed to have any trouble at all. So I used GNU radio tools really for the whole show, and with huge thanks to Tom N5EG, who I know is here at least for the first part of today's presentation. There is a block with drivers that allow GNU radio to interface to the Hermes hardware for both receive and transmit. And the receive side block can run 8 virtual slices simultaneously. So in other words, you could record 8 separate 384 kilohertz segments of spectrum at the same time, which was very cool because I used that to record 80, 40, 30, and 20 meters. I had the red Pitaya, which has a driver that was able to capture 2.5 megahertz of wideband. So that covered the AM broadcast band plus 160 meters. And I had simple flow graphs. I'll show you one of them shortly that simply receive the samples from the radios and dump them to IQ files for later analysis. And then other flow graphs were used later on to process the data. And I also created several custom blocks. They were not out of trees, but just hierarchical blocks, consolidating several existing blocks together just to make the flow chart easier to manage. So this is the data recorder for Hermes, and it's really very straightforward. The big block on the left is the Hermes block, which again has up to 8 receivers available. I used 4, and there was simply the receiver block wired to a bunch of channel sinks. And we used something called digital RF as the file format for recording the data. We could, of course, record the raw GNU radio samples into bin files, but the science community likes the HDF5 digital radio or digital RF format. It's a very hierarchical where each receiving device has a directory that its data goes into. Then under that, there are as a directory, I think, for each like hour, and then another directory for each minute. So ultimately, you end up with lots and lots of small files, but it's very easy to identify them, and you can scroll through the data if you want to look at a specific time. It makes it really easy to zoom in and get to a specific location. And the science folks really wanted us to use HDF5, and there is a set of GNU blocks for that. It's called Digital RF, and you can download the package from the MIT pages. So that was what we used for the blocks on the right-hand side, and that's really the entire recorder, just a source and file syncs, and it didn't have to do anything else beyond that. A couple of other little options to set and things along the way, but basically an extremely simple bit of software for the recording side. I already mentioned the MIT digital RF format. There's the URL for it. It's GitHub MIT Haystack, and it's again become a very widely used format, and seems like a really good one to use for this kind of activity. The laptops had solid state drives, and again, none of them were the fastest machines in the world, but I had no trouble at all recording the data rate. Even the 2.5 megahertz from the Pitaya wasn't a big problem. But that generated a lot of data. Ultimately, it was just under a terabyte, and I ultimately took the data from the 3 computers and merged it onto a single terabyte solid state drive, an external Seagate pocket drive, something like this. And this is the data that we captured. I ran for 8 hours between 1400 and 22 UTC. The total eclipse time was just about in the middle of that shot. So I wanted to get time before and after. And really, if I had done at most 2 hours before and after, that would have been more than enough. But I didn't know when we would start seeing effects. So we thought that capturing 4 hours either side was a good idea. This is the data that we recorded. As you can see, the 4 ham bands, each 384 kilohertz wide, which meant that we could capture the entire 40, 30, and 20 meter band, and also WWV at 10 megahertz. On 80, I was able to get the bottom chunk of the band. I missed out on sideband, but it was hard to get much useful data from sideband signals anyway. Then on AM broadcast, we got 2.5 megahertz centered at 1.4. And then the third radio with the KISS console spectrum analyzer display, tuned to about 28 megs, and grabbed a spectrum plot from DC to 56 megs. That was frankly not all that useful, but it was easy enough to set up. And as you can see, it came just under a terabyte for all of that data. Now the challenge is I've got a terabyte of data. What do I do with it? And it's wideband data with basically narrowband signals in a long time period. A waterfall has some limitations, and this steps to make previous slide is I got out of order. I discovered that my flow charts had both, some of them disappeared and I had to recreate them, and others uh, uh, were broken by 399, and I wasn't able to get everything I wanted running. But we did waterfalls, and then I did a couple of ways to take individual snapshots of graphs and save those as PNGs and turn them into animations. And you'll see one of those a little bit later. And that was a way to concentrate 8 hours of data into about 3 minutes. It was very useful to get an impression. But again, with narrowband signals, it's really hard to pick much out of that much data. So there are different tools really that you'd want to use. This was the script for doing a playback of the HDF5, and this was uh, basically taking one receive channel, the digital RF source on the left, going through a throttle, frequency translating filter to a frequency sync. And then the frequency sync, literally I grabbed a screenshot every, I think, 30 seconds of the FFT display, and then stitched that together with FFmpeg to make a single animated MP4. And I think I do have that a little bit later here in the presentation. I wanted to do a long duration waterfall to see the Doppler shift, particularly at 10 megahertz WWV. And that was an interesting challenge because I learned that the waterfall sync in the GNU Radio's QT toolkit only could have a limited number of lines, and it didn't scroll. So there's no way to capture more than a single shot. So what I did was a lot of experiments to get a decimation rate. So the length of the playback time, the amount of decimation, and the FFT width gave me just enough rows of data to fill the display, which is about 1,200 lines. So I just kind of worked everything backwards to get the data that I wanted to fit into 400 FFTs, each making, I'm sorry, it had 1,200 FFTs to make up the frame. And here I decimated the original data down to about 4 and some fraction samples per second. And an FFT of 1023, and then trim that down to about 6 hours, 40 minutes, just because that's what would fit. And so it was a 2-minute frame. And this is the result for 10 megahertz. And the question is, was there a Doppler shift? The red line is when the maximum obscuration showed up at my location. And if you look just before that, you see a blip of yellow to the lower, and then if you squint a little bit, you can see that it seems to go off to the right, and that is a Doppler signature of the WWV carrier being shifted as the ionosphere moved up and down due to the effects of the solar energy not being there. We were able to capture that couple of hertz of short-term Doppler shift. But again, it was a painful tool to do. There's got to be a better way. And I will say, working with the HamSci people, one of the things that amazed me as an old timer is what the current crop of students and grad assistants are able to do with data visualization tools. Using a number of Python tools. They do stuff that is just incredible to show this data off, and I completely lack those skills. So part of my real hope when I recorded this was that somebody would take the data and then really go through it and see what they could wring out of it with those kinds of tools compared to the very primitive stuff that I was doing. Another thing I wanted to look at was how to measure the amplitude. And I got these slides out of order, I'm afraid, because I'm going to show you the slide next. It's not the previous. But I took the data for the 10 megahertz area around WWV, and decimated it down to get one FFT every 15 seconds. And then I read that FFT to get the bin with the maximum value and write the maximum value to disk file. So what I ended up with was every 15 seconds, I had a dB full scale reading of the WWV carrier over the 8-hour period. And then I used a tool called Grace to plot that. And I don't know if any of you are familiar with it. It's quite an old piece of software now, but it's a Unix-based tool that was developed by a university in Israel that I've found to be quite useful for doing simple plotting tasks. It's got a GUI interface, so it's a bit more intuitive to use than GNU plot. It has some limitations, but it's capable of doing quite a lot. So I generated this plot from that data using what I showed above. Again, the vertical line is when the Eclipse Max was there. And if I squint, I can say that it seems like there was less noise and a more stable amplitude from about the time of maximum obscuration for another hour and a half after that. But I don't really know if that was an eclipse effect or just natural variation. So I don't know that there's anything that came out of this data that's meaningful, but there is a bit of quieting, it looks like, where the amplitude is more stable during the eclipse period. So then I moved on to the broadcast band recording. And again, what do we do with that? So I had 8 hours of 2.5 megasample data. The Pitaya also had some challenges. I couldn't lock it to an external reference. It's possible to do that to the Pitaya, but it's not straightforward. You have to do surgery to the board, and you have to feed in, I think it's a 64 or 128 megahertz signal. You can't just pump in 10 megs to make it easy. So in order to try to mitigate any kind of frequency drift that we would have, because the receiver was actually sitting out on our rear deck where it was in sunlight sometimes and shade others, I injected a pilot signal that was derived from the atomic standard at 1850 kilohertz. So if I ever did want to try to do any frequency measurements, I could compare against that constant signal to compensate for any drift that might have happened. And the front end of the Pitaya wasn't a good match for 50 ohms. And I think anybody who's used it has probably seen that folks have made transformers and various kinds of front end improvements. But a random wire is not a very good match for 50 ohms either. And with broadcast band, it's really the noise level that's the issue, not sensitivity. So I didn't pay much attention to worrying about the antenna match on the Pitaya. So first, we wanted to look at what the entire spectrum looked like. So I played it back into an FFT and again captured one frame every X seconds and then assembled those into a movie. And then I sat back and made some popcorn to watch. And hopefully I'm going to be able to make this movie. Oh, crap, that didn't work. So this was an animation looking at the broadcast band, the 1850 signal you could see off near the right as the pilot. And it was 1 minute with a flashing tint to show the totality. What you would have seen is signals bouncing up around that time. There definitely was enhanced propagation. And I'll try to play this at the end if we have time. But the problem is that that's interesting, but again, it's looking at a huge amount of data over a long period of time, and it's hard to get much objective data out of that as is. So the idea that I had, excuse me, was to break the band into channels. I think there are about 115 AM broadcast channels in the US at 10 kilohertz spacing. Separate each channel out and put a very narrow filter on the center of the channel to look at the carrier if there was a broadcast station present, and then log the amplitude and also the frequency offset to catch any kind of Doppler effects. to a file. Then when that was finished, I munged the data a little bit and picked the 10 channels that had the most variation between the minimum and the maximum that we saw. My thinking was that that was likely to be a propagation impact if we had the biggest shift from min to max, and then plot the amplitude and frequency variation over time, and ultimately make a movie of that. Unfortunately, that movie is also broken, but this is the flow graph. On the left is a polyphase filter with 125 channels, and then lots and lots of other blocks. This is a zoom in of what it would look like just doing 10 channels. So polyphase filter bank, creating virtual sources, then feeding that into a block that basically was looking for the maximum power in an FFT bin, or I think it was about a 50 hertz wide bin that we were looking at, and that logged that to disk. And this was a very interesting way to learn about the polyphase filter. Nothing like diving it head first. Doing 2 or 3 channels is simple, but 115 made it worthwhile. Once you understand it, it actually is pretty easy to use the polyphase filter. The difficulty is that I was really unable to find anybody who had a tutorial that I could understand. Back a number of years ago, who was the prior maintainer? I was Tom, I want to say Tom Shepard, but that's not right.
Tom Rondeau.
Tom Rondeau, yes, thank you. Posted an article about how to do it, but he assumed that everybody had like calculus and understood signal processing theory, and I'm not either of those things. So I wasn't really able to get much from it. But the magic is you have to create a map of the channels. And when you do the polyphase filter, you don't end up with something as simple as the lowest frequency on channel 0 and the highest on channel N. There's an interleaving toward the center. So you have to build a map that basically goes from halfway through to 0 and then out to halfway again with the channel numbering. And you also have to have a low-pass filter design that will generate the bandwidths that you want with the right kind of skirts. But once you understand how to generate the filter and how to make the channel map, then the polyphase filter is an incredible tool. And I've got another flowchart at the end that I'll show that it shows another application for that. We used this times 12, basically what you're seeing on the screen now, to generate a file for every AM broadcast band channel from 550 to I think it's 1650 now, or maybe 1700, and capture the amplitude in that file every so often during the entire time. And let's see. Okay, this was the maximum power sink that I came up with. Basically, you take a sample stream coming in, make a decimating FIR filter, then do a log power FFT, and then capture the max from the FFT and just dump that to a file sink. So very straightforward. What I then did was I created this block, then I created a hierarchical block with 10 of these in a single block, just to make it easier to place in the flow graph. So instead of having 125 of these, now I have 12. So that was one trick to simplify the huge flow graph, was using hierarchical blocks to consolidate repeated elements into a single block, just to make things easier to look at. This is a channel power sink that measured the total power within the channel. Same kind of idea, but instead of looking at just the carrier, it was looking at a broader bandwidth. And then this is taking the channel power sink and just putting 10 of them into a single hierarchical block. So this is the result, and it is, I think, quite interesting. These are the top 10 stations, the top 10 frequencies rather, that uh, showed the maximum difference between minimum and maximum amplitude over the 8-hour period. So it's plotted, the x-axis is time, the y-axis is the channel power and a 50 hertz bandwidth. So I wanted to look at the very narrow bandwidth because I didn't want any kind of modulation to impact the results. So at 50 hertz, it was generally filtering out all of the voice or other modulation on the signal and just capturing the carrier. And you can see that there was a significant increase in amplitude prior to the maximum local obscuration, and then a fairly rapid drop off afterwards. And you see 9 of the 10 channels behave that way, but the 10th channel had a big drop during that period. And if I remember right, the blue channel that was the lowest drop was at 1510 kilohertz. And I was wondering if maybe it being at the higher frequency that had an impact, but I really don't have an explanation for why this happened. But it certainly should mean something to see one channel that literally did the opposite of what the other 9 did. So I hope someday one of these space physicists will look at this and figure it out. But my goal was just to see if I could make the pretty chart, and I think I succeeded doing that. Then there was another idea that I had that initially I thought was absolutely impossible, but what about taking all that band data that I recorded and try to actually analyze the signals that were recorded and look at the CW signals in particular and try to capture some information that would let us see trends. So the idea was to use the CW Skimmer software that Alex, VE3EDA, makes available. And this is what runs the reverse beacon network. Basically, you hook the skimmer up to a software-defined radio's IQ stream, and it scans the bandwidth, looks for signals, and decodes the Morse, and outputs a text stream for each signal that it finds. And with some help from Rick N1GP, we figured out a way to take the binary file from GNU Radio, feed it through a Raspberry Pi that acted kind of as a shim to simulate an HPSDR channel, and then feed that into the skimmer. And again, Rick is the one who really came up with the tool to make that work. So I did that and looked at the 5 bands that we had recorded, 80, 40, 30, and 20. Well, there was nothing on 160, and 30 meters had very minimal activity. It wasn't part of the QSO party. So I focused on 80, 40, and 20. And we were able to get a lot of data on 80, almost 1,800 spots and 70 calls. On 40, 7,700 spots and 286 calls. On 20, 12,000 spots and 333 calls. So we gathered all that data, and from that we're able to generate a lot of interesting tables. So here is the number of spots per minute on each band, and you can see that 20 meters had probably a dip around and after the time of maximum, whereas both 80 and 40 had peaked both at about maximum, but then about a few hours after, I'm sorry, about 3 minutes, about 5 hours afterwards, another peak, and then a very rapid fall off. So again, we can see that there's definitely an impact. And again, the idea is, if you think about it, we're creating a nighttime condition by having the solar wind not hitting the ionosphere suddenly. So we would expect that to enhance propagation at low frequencies, but also diminish it at high frequencies, the same way as 80 and 40 are better at night. And we can see that here, that we see 80 and 40 definitely had an enhancement that lasted quite a long time, whereas 20, if anything, had a dip around that time. And then this is looking at the average signal to noise ratio. Again, the same thing. And here, again, look at how 80 improved with the blue line, whereas 40 and 20, stayed about the same. So again, we can see a much bigger impact on 80. Why 40 is flat when it showed an increase in activity, I'm not quite sure. The two different aspects of amplitude and just the number of call signs logged showed some difference there. Then looking at each band, this is the signal to noise ratio and the histogram, the number of calls per minute for 80, 40, and 20. And again, here we can see the signal strength on 20 has dipped, where 80, I'm sorry, what were yeah, 20 meters. The number of spots dipped significantly. The signal strength seems to have dipped on 40, kind of flat, but you can see an increase in activity. On 80, everything closely tied to the impact of the obscuration. We were able to then log the most prolific senders that we recorded during that time. So I don't know if this was a real contest or not, but congratulations to K9DX, NAPW, W0ERE, and N4BP, because we heard them more than anybody else up in northern Lake Michigan. So yeah, after all of that, it's clear that SDR systems let us capture an enormous amount of data about propagation. And it's a really good thing that disks have gotten so cheap, because doing a terabyte in a day was not a real challenge with this experiment. The analysis is much harder than the recording. And again, I really like somebody who's a data scientist to take what I have and really look at ways to dig meaning out of it and to visualize it in better ways. Playing back at a higher speed would limit things. When I recorded an animation, it took me almost 8 hours to record all the snapshots of the FFT during that time. There was no way to really speed it up practically. There are probably ways that we could double the apparent speed or quadruple it to reduce the time that it took to record. And then figure out the best tools to look at these narrow signals and wide bandwidth over a long time. I'm not sure what the right approach is there. The Red Papaya was really quite impressive, giving a 14-bit receiver for less than $300. This is kind of obsolete information now, because there's been a new version of the Red Papaya since this that does have a better input match. And I think they also have a 16-bit version available now. And I think they've also made it a bit easier to do external frequency reference. That was a neat piece of hardware with a lot of performance for a low price. I think, though, the next time around, and again, it wasn't available when I made these slides originally, but I think the Kiwi SDR is an obvious tool to use for this the next time around, because of its ability to grab slices of data and at an even lower cost. And I'm waiting for 2024 when we can do this again and have some new tools set up. And I just wanted to take a second to show a couple of other tricks that I do with GNU Radio that you might find interesting. So I've got all this live data recorded, an IQ that's just like it was off the air. What else can we do with it? Well, at Dayton Hamvention, Tapper, when that's an organization that I'm heavily involved with, usually has a bunch of SDRs on the table to show off. And the difficulty is at Hera Arena, the old location for Hamvention in Dayton, and the new Greene County Fairgrounds location, the metal buildings shield just about all signals from getting inside. It was almost impossible to hear anything other than an AM station or two. So for about the last 4 years, I created our own test signals by taking recorded band data and then just taking the file. It was a bin file recorded with just the standard file sync, playing it back through a throttle block to set the rate, multiply to crank the gain up, and then feed that into a USRP. So I was able to play 40 meters or 20 meters back at 145 megahertz if I wanted, or at 51 megahertz. And that worked really well. We had the USRP running with a little gain block, probably generating a total power over 300 kilohertz of maybe 10 milliwatts, so not a lot of power, and just a wire antenna that ran underneath the tables where the radios were. And we were able to get a really a usable signal from that. So just think of the fun that you can have if you record a bunch of DX and then play it back on 6 meters for your friends, and let them think that there's the best opening they've ever heard. And I'm not responsible if the FCC finds you doing it. That's your problem. But it actually works extremely well to play back the live data to use for as a test signal for other purposes. And then here's another example of using the polyphase filter. This is a 7-channel FM receiver that will pick up 7 narrowband FM channels on the 2-meter band simultaneously, apply a squelch to them, then FM demodulate and feed them into an adder that drives a sound source, or a file sync for that matter. And what you can do with this is monitor 7 channels at once. If any of them come live, you'll hear the audio. You can also have a visual display to show which channel the squelch is open on. And if you want, you can record each channel to its own audio disk file with the squelch starting and stopping the recording. So that was a really neat application of the polyphase filter bank. It's a little bit easier to map with 7 channels than 125. And again, I took advantage of the virtual sources and sinks to make this flow graph possible to read. And the blocks on the right are really just 7 instances of an FM receiver being fed by the virtual streams, and then they all feed into a single adder block, and then into the audio, a rational resampler for the audio rate, and then a gain block and output. And I had at one point had this working for 21 channels. The idea was to be able to capture all of the FM repeater outputs in the US 2-meter band. And I sort of had that working, but I was beginning to run into some problems with handling combining the audio together at the output from that many channels. It's probably not feasible to multiplex the audio, but if you ran everything into its own file for playback later, you could literally capture the entire band. Every output channel is demodulated audio. So that's about it. I'll close you with just Bunny the Eclipse cat tells you to always protect your eyes. The next solar eclipse in the US is 2024. I think there's another one in Europe, if not later this year, maybe next year. So there are other opportunities around. And that's all. So thank you very much. And I will unshare. Okay.
Great. Thank you very much, John.
You're very welcome. I'm happy to take any questions. I don't know that I can answer them, but
there's a few that have come up in chat, and so we can scan down those. I think there's been some discussion, but it's good to ask them anyways. Starting off with your polyphase filter arrangement had a bunch of virtual source and virtual sinks.
Mm-hmm.
I think that was specifically asking about your 10-channel example, but if you could flip back to your larger example, I saw that you were using some null sinks as well.
Yes, and I'm trying to figure out how I can get back there. I can't find it now, but yes, the null sync was very useful for cases where you had an unused output from the polyphase filter to keep GNU Radio from throwing an exception because it was missing a wire. The null sync is a way that you can terminate unused output ports. And it was very useful for cases where I wasn't able to use the entire output range from the filter. And also with the polyphase filter, you can't just have an arbitrary number of channels. You have to pick a channel map that divides into the sample rate. And as a result, instead of, I think, 115 channels would cover the entire AM band. I think I had to do the channelizer for 125 channels to get the math to work out right, to fully swallow the 2.5 megasample input stream. So you don't have total flexibility with the polyphase filter for how you can implement it. And if you have to generate more channels than you need, the null sink is a way to then terminate the extras and keep the GRC happy.
That makes sense. My response in the chat was it would be a nice feature for the GNU radio block to support disabling outputs. So if you say, these are the channels that I actually care about, you can get the efficiency of the polyphase math to do that even division, but then just completely ignore the unused channels and skip that, the need for those null sinks.
Yeah.
And if that hasn't happened in the last 4 years, then we'll put up an issue saying that that would be a nice improvement. In Spectrum was suggested as a way to view the long-term spectrum. Have you ever used in Spectrum?
No, I haven't.
So it's a piece of software developed by Mike Walters here in the United Kingdom. He's up in Scotland, and it's capable of opening up IQ files and visualizing them. I don't know how well it responds to a 100 gigabyte file, but it reminds me of another tool called Baudline, which was expressly designed for dealing with extremely large data sets. So it could be two tools to take a look at.
Okay, that's good to know. I've also learned a tiny bit about some of the Python tools, and I haven't brought them to bear on the Eclipse data, but for the project I was doing, trying to plot performance of GPS receivers, Phil Erickson, W1JPE, or no, PJE, showed me there's a specialized toolkit called, I think it's AstroPy, something like that, but it's a scientific astronomic astronomy oriented toolkit that sits on top of Matplot and some of the other lower level tools, and makes it very easy to pull graphs, and you can do 3-dimensional x-axis, y-axis, z-axis stuff. So I think there are definitely tools that are out there. It's just my knowledge of how to use them was so limited that I really didn't know the best way to do it. And I think somebody could take this data and really do a lot of other interesting stuff with it. And if anybody wants it, I'm happy to make it available, the raw data, to anybody who would like to play with it.
That was going to be one of my questions, was where is the data now, and is there any way of getting access to it?
It's on here and a couple of backups. And to be honest, the easiest way to get access to it, if you want the whole thing, would be for me to literally to ship a solid state drive. Now, if you want to just say 20 meters, well, that's under 100 gigs. So that's something that you might be able to feasibly download. The AM broadcast was by far the biggest chunk. That was about 500 gigs. So you could reduce it, but if anybody wants to send me a solid state drive, to a terabyte drive to put on, I would be happy to copy it to them and send it back.
Great. Christoph, ON1ARF asked, how long did the solar eclipse actually take, the total solar eclipse?
It was across the US for about 4 hours. It came in from the Pacific Northwest, swung down, and in the mid-US passed down around kind of, I think, southern Kentucky, and then swept over to the Atlantic seaboard. So about 4 hours total. The total duration, the length of the totality, of course, technically it's instantaneous because it's only going to be perfect, just once. but the total time, if you were in that area, was a few minutes when the sun was totally obscured. Where I was, it never got to be more than about 70% obscured because I was so far out of the path. But I was able to notice a darkening of the sky when that was happening, and it was kind of apparent for maybe 10 minutes where I was that it had gotten a little bit darker. So the actual maximum time is quite short. However, the propagation effects were long lasting because as the D&E layers are affected, they build or they break up. They don't do that instantly. So there's inertia in the propagation, so it doesn't react nearly as fast as the actual change in the amount of daylight.
Cool. Clayton, VE3 IRR asks, are there already plans in the works for the 2024 eclipse?
Yes, indeed there are. And if you're interested in this, please go to the HamSci webpage. It's hamsci.org. And you will find some information there. Christina Collins, and I can't remember Christina's name, but she is a grad student at Case Western and has been very actively involved, is leading efforts, not just for the 2024 eclipse, but for the one that we had earlier this year that was, I think, in Europe and Southern Hemisphere. So she's working on that. And I should put in a plug for the a bigger HamSci project. We are working, HamSci has gotten much more formalized. Nathaniel has moved to University of Scranton in Pennsylvania. He got an NSF grant of many hundreds of thousands of dollars to basically go toward the citizen science stuff. And so we have a much bigger organization now and some money to spend. Tapper is designing a personal space weather station, which is really an SDR that's specifically designed for scientific applications as well as normal ham radio use, that will be going out to as many people as we can get it to allow scientists to be able to get at data. If something interesting happens, if there's a solar flare, and when this thing's up and running, a scientist will actually be able to go out and say, everybody who has data recorded between 5 and 10 megahertz for this time period, please flag it. And then they can arrange for that to automatically be uploaded to the central database and provide access to the scientists for evaluation. So it's a really cool project, and HamSci is sponsoring that. Tapper is doing the engineering, and within that, I'm doing the GPS decimal oscillator module that will go into that. There's another project for a lower cost device. It's called a GRAPE, and I can't remember what that stands for, but it's a receiver designed to be very low cost in the kind of $100 range that will receive 4 standard time stations simultaneously and generate an output that can be fed into a sound card to log Doppler shift against WWV. So you could listen to 2.5, 5, 10, 15, or whatever, and capture the Doppler effects day by day with that. So that will be a lower cost tool. And again, Christina has been heavily involved in the engineering of that. Case Western is basically running that project. So that's a lower cost device. The Tangerine SDR, which is what Tapper's calling our project, will end up being a $500 to $1,000, depending on how tricked out it is, system. But we're trying to have both a low end and a more capable scientific system available.
Great. Yeah, that's Christina Collins, KD8OXT.
Thank you.
And I know with my university hat on here, Cardiff University is hoping to be the first overseas station as part of the network there.
All right.
We're looking forward to it. And Bernard Tyres has just posted into chat. That's hamsci.org/projects to find out more information from the HamSci side. And then HamSci had their annual conference quite recently, I think.
Yes, they've sponsored a conference for, I think, 4 years now. The last two were virtual because of the unpleasantness, and they actually went over very well. And one of the things that we found, and I think today's meeting is an example, it's a bummer not to be able to see people in person and have that kind of interaction. But the Zoom-based conferences, you can get much greater attendance and you can get much more worldwide attendance. And we saw that with the HamSci conference had twice as many people as they did when it was a live event. And the information exchange was really good. If you're interested in this kind of stuff at all, I really can't recommend looking at the HamSci group. They're just doing a lot of really cool stuff.
I'm definitely hoping we get some HamSci submissions to GNU Radio Conference this fall.
That would be great.
And I suppose this is a good chance to plug both Taproot's Digital Communications Conference and GNU Radio's conference are going to be running the same week.
I think so. We're going to be virtual.
Okay.
We just made that decision, and I think we're looking at keeping the same weekend dates, which, if I remember, are around September 16, 17.
Yeah.
And then I think GNU Radio follows immediately after that.
So we'll be running 20 through 24th of September.
Okay. Well, then maybe I may be off by a week then.
And this is our first public announcement, I guess. Don't go screaming it on the web quite yet, but we will be running an in-person event this fall. But as you said, there's just been such a good response to live streaming and making things remotely accessible. GNU Radio Conference, had over 1,600, almost 1,700 attendees last year. So we will definitely be live streaming and keeping the virtual side as well.
Yeah, we just made the decision to stay virtual. We did an online survey, and a very large number of the people who responded indicated that whether because of COVID or for other reasons, they would not attend in person. So we just were afraid that we wouldn't have enough folks there, and things were still uncertain enough. So we're going to stick with virtual this year and then go back next year back to live. We're also going to have to actually try to have a live virtual combined somehow if we can make that work.
But I definitely hope we stay in touch over the next year then, because this year we were hoping to be in the same location, and then COVID just hit last year and then this year. So but it just makes so much sense to run both events at the same place.
Yeah, the overlap is just huge. And I guess I'll put in the plug. The Tapper Digital Communications Conference is what we're talking about in addition to GNU Radio. We've been running it for under a couple of different names for I think close to 40 years now. And it runs on Friday and Saturday. And then when we were doing a live Sunday morning would be a hands-on tutorial seminar kind of show. And we got a tremendous number of high quality papers and presentations around kind of anything related to computers and radio. It was a very broad charter from Phil Karn explaining error correction technologies to people showing how they're using spread spectrum Wi-Fi stuff to do marathon communications. So a very broad range, but really smart people and very good content there every year. And we're tapper.org if you're interested.
Jumping back to your topic, Christoph had a follow-up question asking, would it be interesting to do the same measurement when there's no solar eclipse to have a good reference?
There have been some measurements done like that, particularly some of the Doppler experiments people ran before the eclipse and after. So yeah, having that control is good, although the problem is the ionosphere is never the same 2 days in a row. So you almost need to have a lot of long-term data to know what the mean really is, to look at the difference, because if you just look a day prior, there could have been a flare or something that changed it completely.
I guess that's
But having
something.
control data is really valuable.
I guess that's something that the personal space weather station really would be in a position to
Yes,
provide.
yes, it would.
Jam was asking, is there a URL for the timing station reception project?
It should be at the HAMSI page, the projects page that came up, and just look for GRAPES, grapes as the name of the receiver project.
He follows up saying he's measuring DCF 77 from Germany, TDF in France, MSG, MSG, not the food additive, in England, MSF, and Loran with a sound card already.
Yeah. And one of the things that I had thought about doing, but I just wasn't able to arrange, would be to monitor, say, WWVB during the eclipse and see what the impact was on the very long wave 60 kilohertz propagation. And I don't know if anybody has actually done that to look at that through the eclipse. So that could be an area for some further research next time around.
Great. That's the end of the questions from the chat. I have turned off the everyone can unmute if they wish and ask questions directly. Otherwise, we'll thank John and go into kind of open chat.
Okay, I guess I've stunned them into silence.
It's the way it usually goes. So yes, already happening in chat, but thank you very much, John. Very much appreciated for the talk, and hopefully some of the folks here will jump on and help out with some of these personal space weather station projects. And Bernard Tyers did post a link for eclipses occurring here in Europe, and I've lost the link myself now, but there's a variety of them coming up over the next couple of years, including a general partial one covering all of Europe next October. So stuff to look forward to.
And just one last thing, Derek, since my animations didn't work, when I have a chance, I'm going to try to get all these scripts updated for 3.9. That was my other challenge this week. I discovered that GNU Radio had disappeared off this computer, and when I went to install it from packages rather than building it myself, I ended up with 3.9 and everything broke. But once I get some of those things fixed, I will try to get all the Eclipse related tools up on GitHub. My GitHub is just N8UR, or some of my stuff is under the Tapper GitHub at TAPR, and I will upload the animations there when I have them actually working properly.
Wonderful. And both for yourself, for Tom, and for anyone else in the chat here, if you're ever having a problem porting between versions, please do drop a note either on the email list or our chat room at chat.gnuradio.org. And there's always folks around who can at least give hints, if not do the full porting. So.
Yeah, so far the biggest problem I've had has been blocks that have disappeared, and also the fact that all the filter taps have changed. I used to have a low pass filter variable that had the equation, and that all those broke. I had to go and get the new low pass tap blocks and bring it in and transfer the parameters into that. But the other part has just been along the way, several of the hierarchical blocks I built have disappeared. So I've got to go back and reconstruct those.
Yeah, stable code over years is still an aspirational goal for GNU Radio, I think. Grand. Well, thanks very much. And I guess we'll close the main talk there.